So let's we begin with. So today we have a target to understand about the characteristic of a diode or a PN junction when it is in forward bias condition, when it is in a reverse bias condition, and when it has no bias. It means the zero bias state. So whenever we talk about the effect of flow of current when we are applying a voltage, that all depends on one thing, what kind of a biasing you are using. So this process is called as a bias, and bias it means the arrangement of circuitry, the arrangement of flow of charge carrier, the arrangement of diode kind of a device is called as a biasing. So this biasing is very important while we are going to utilize this semiconductor device. Not only simply we are talking about a diode, but every device which is made up of semiconductor material, that all depends upon what kind of a circuit arrangement you are doing. That's all totally depend on the circuit arrangement. So that's why it's important here to understand that. In this section, we have a target. So let's just have an idea to try to understand that if suppose we are providing certain voltage, whether in an opposite favor, whether in a favorable condition, whether we are providing a reverse, whether we are providing a forward, that all matters. So while we are just considering this one, so under this consideration that matters that how we are providing and what will be the effect. So important point. So let's begin with this one. So first of all, let's go with this previous slide. If you see here, we have just taken basically an arrangement. This kind of arrangement is here. If you see, it's a very kind of a simple experiment is here. On this experiment, we basically are using the 2 voltmeters and 1 ammeter. So this voltmeter is basically giving us an idea the voltage across the diode. It's very important phenomenon, because it's not only the characteristic of a diode, a very important phenomena is associated with this one. So just take it very seriously and carefully. So the first that we see here, it is basically a voltmeter connected just across the diode. It means it is just giving the potential drop. Important point. This is potential drop. It is showing the potential drop across the diode. And here, if we see here, we have a voltage which is being applied. So this is the drop voltage which is going to be measured. And here is the voltage which is applied. This is a supply voltage. So this voltmeter is doing just only measuring one thing, which is the applied voltage. So this is a bias voltage. If you see here, we have one ammeter, and this ammeter is being printed with the word IF. So this IF is indicating that this is the forward bias current. So under this forward bias situation, this shows you the IF. And looking for the reverse bias situation, it shows the reverse bias current. So under all this one, this matters, like important part is here, that how this diode is taken care by. So here we see the 2 voltmeters and 1 ammeter. And here this is showing the drop, and here it is showing basically the applied voltage. So the applied voltages are here, which is basically the biasing voltage. The voltage across the diode is called as a forward bias voltage, and the current flowing through these wires is called as basically forward bias current. Now we try to understand what is happening about that. So if we go back and see these slides, so we understand naturally when diodes, it means the PN junction is framed, we have a certain depletion region. And at this depletion region, we have basically a potential barrier. A barrier has been created, which is opposing the further movement of charge carriers from N to P and P to N. Now while we are applying certain voltage across this one, so while we are applying voltage across this diode, so we have to take care about that, whether this voltage is supporting this potential barrier or opposing the potential barrier. If suppose it is supporting the potential barrier, in the situation, the potential barrier will be increasing. And if it is opposing the potential barrier, then the potential barrier will be reducing. So if we see in the next diagram, so as we are providing here, this bias voltage and some voltage already produced over here. So I just tell you if suppose we have a germanium, we have a silicon. So in silicon and germanium, in both type of semiconductor material, if we are making a silicon semiconductor PN junction, we have 0.7 volt as a potential barrier. That's important. So take care about that. 0.7 volt we have as a potential barrier. And while we are using a germanium, we have 0.3 volt as a potential barrier. So suppose when this voltage is being applied, and if this voltage is only 0.1 volt, applied voltage is only 0.1 volt, it will not create any effect because the potential barrier still remains. When we are increasing this more than 0.7, then we are increasing this more than 0.7, then this potential barrier will be completely vanished out, and then after there is a start of flow of current, and we will be having some current on this ammeter. So that's why if we see here, such situation appears. We have here on this y-axis IF, which is the forward bias current we have taken previously. Here in this we have this VF, important. So this is not bias voltage. On this axis what we are taking? We are taking VF. VF means the voltage across diode. What exactly it is? This is a voltage across diode. So if we see, suppose that we are increasing, if see, you see here zero bias. When this is zero bias, so this comes on a dot situation. It means no flow of current. Under zero bias situation, we have no flow of current at this situation. There is no flow. But as we are increasing biasing voltage, a small, almost small, or we can say a negligible current starts flowing. This negligible current keep on flowing negligible until the bias voltage reaches to 0.7. When it reaches to 0.7 volt, suppose external voltage we are increasing more. When it reaches to 0.7 volt, then the current will start increasing because the potential barrier has been removed completely. And when this potential barrier is removed completely, the diode has only a potential drop of 0.7 volt, and then further there is no improvement, there is no further any sort of the increase in the potential drop, and current is keep on increasing. Current बढ़ता ही जाएगा. If you see here, this current is keep on increasing. So this current is increasing, but the potential drop is not increasing because the junction has now no barrier, no obstruction is here. So this situation called as a forward bias. So if we see here from zero bias to, if we are increasing voltage, the potential drop across the diode is keep on increasing, but after some time, a potential drop will stop. It will become 0.7 volts, and then after there will be no further drop across the diode, and this will show the increase in the current. Now if you see here, under this situation, what is happening? So we go for this second diagram. This second diagram is indicating the resistance, which is called as a diode resistance or the dynamic resistance. We see here the resistance varies continuously. If we see here the potential, if we see here the difference in the current, we see the change in the voltage. So initially the change in voltage and the change in current, delta VF, change in voltage is much, but the change in current is so low. So initially this VF upon IF is too high because this resistance is depending upon VF divided by I. So as much VF we have, definitely the resistance will be more. But with respect to time, if you see here in this diagram, this potential difference is low and current is increasing. So this shows the diode offers low resistance from this point to this point. And further, if you go on increasing, you will see here the change in voltage drop is almost reducing, but the change in current is increasing. So if we see here under this third step, in the third state, we check that this resistance is now decreasing and the current is increasing. So that is a very common phenomena if we talk about. The current is inversely proportional to resistance. If resistance is higher, the current will be low. If the resistance is low, the current will be higher. And who is the main responsible factor who is deciding this current? Basically, the depletion region. So the depletion region is the main factor who is deciding, who is creating this situation. And this situation is basically called as, that this is offering a resistance when it is in forward bias, and now it is not offering any resistance when it is completely forward bias. So we have to take care about this. So the voltage which is required to remove, important, the voltage which is required to remove potential barrier is called as a knee voltage. It's called as knee voltage. So here this 0.7 volt is the knee voltage in the case of silicon and 0.3 volt in the case of germanium. So this is exactly the meaning of it. And from 0 bias, if suppose we are increasing this voltage from 0 bias, and after some time, if you see here, this voltage drop becomes almost constant. The voltage is not further increasing, but the current is increasing. What exactly that means? Why this is here? This is my question. Let me explain. Let you explain. So now coming on a very, very important topic. And this topic is not only related with this diode characteristic, but this is a general conception. General conception. See, what exactly the voltage drop? The voltage drop is nothing but it is basically an offered wastage of energy across the path of current. Offered wastage of energy. So this is called as a drop. Drop. Suppose that you have a 220 volt supply at your home and it is reaching to your electric bulb only 200. So where is this 30 volt? So 30 volt, we say it is a drop in wire. So the drop in wire is what? Exactly that shows this is basically a loss factor. It means that has been lost by the particular wires. Same case happens in the case of a diode, but in our diode we have a great feature. What is that? Varying conductivity or varying resistivity. Both the words are common. You can say varying conductivity, you can say the varying resistivity. This is exactly basically the beauty of the semiconductors. We see here in our semiconductor, conductivity and the resistivity is not fixed. Come back on this one. The conductivity and the resistivity is not fixed, it's continuously varying. Initially, when depletion region was there, some resistance were offered during that position. And when there is a resistance, then only there is a drop. When there is a resistance, then only there is a drop. You were telling almost right, but you were not changing the reference. Rather than finding out the reference for the resistance, take the reference for the voltage. Reference जो हमें लेना है वो voltage का reference लेना है, ना कि resistance का reference लेना. हुआ क्या? Suppose that we have here something. Resistance is here. This is the depletion region, and we have a depletion region. Definitely, it has a resistance. While this depletion region is decreasing, it means the obstruction posed by is decreasing continuously. When this obstruction posed by is decreasing continuously, if we go for V equals to IR, under this situation, when R is decreasing, then potential drop V is also decreasing. R is decreasing, then potential drop is decreasing. After some time, when there is no depletion region, ideally, अब मैं बात करता हूँ यहाँ पर ideally जब depletion region नहीं होगा, इसका मतलब कोई रुकावट नहीं है. रुकावट नहीं है तो कोई obstruction नहीं है. Obstruction नहीं है तो resistance नहीं है, और resistance नहीं है तो V equals to IR के according. Now हम जो reference ले रहे थे वो R की reference ले रहे थे. Reference लेना V का. V equals to IR के according. Now the potential drop V equals to IR के according, potential drop becomes 0. So this potential drop, if you see here, initially when there were no outside voltage, कोई voltage नहीं था, 0 bias था, so this potential drop was almost 0. अब voltage लगाना start किया. When we are applying this voltage across the diode, it starts absorbing. उसने क्या किया? बाहर वाले voltage को absorb करना start किया, loss create करना start किया. And that keep on increasing और increase होता गया. जैसे जैसे हमने बाहर से voltage बढ़ाया, वैसे वैसे diode के across VF जो voltage था, this is this one, this VF voltage. Diode के across जो VF voltage था वो drop बढ़ता गया. क्यों बढ़ता गया? Because at that time it is fighting against. किसके लिए fight कर रहा है? It is fighting against to overcome this depletion. To overcome this depletion. इस depletion को हटाने के लिए it is fighting on. ये fight कर रहा है. अब जैसे ही ये वोल्टेज 0.7 वोल्ट के पास पहुंचता है, बाहर वाला वोल्टेज, it has absorbed 0.7 volt and fought against the depletion region and vanished out the depletion. ये depletion के against fight कर लिया इसने, उसको vanish out कर दिया। अब इसको और वोल्टेज नहीं चाहिए, किसके लिए? depletion region को हटाने के लिए। That has already been removed. अब removed हो गई, करंट के रास्ते में कोई रुकावट नहीं है, there is no obstruction। जब कोई रुकावट नहीं है किसी तरीके की, तो अब जंक्शन पे कोई रेजिस्टेंस का ड्रॉप ही नहीं होगा। क्यों? क्योंकि उसको तो ड्रॉप इसलिए चाहिए था ना, वेस्टेज ऑफ एनर्जी थी डिप्लीशन को हटाने के लिए। जब वो डिप्लीशन हट ही गया, there is a continuous flow of the charge carriers, now it does not require anyone. So ideally there is no further drop, but because of the lattice, because there is always a lattice, जब भी lattice होगा तो कुछ ना कुछ हल्का मूवमेंट रहेगा। So that's why if you see here, this curve have a slight inclined portion, थोड़ा सा inclined है, so it shows a very small drop keep on increasing। इस वजह से 0.7 से थोड़ा होता है। And when junction becomes almost clear, then there is a complete continuous flow of current, and as you are increasing the voltage, junction को voltage नहीं चाहिए, आप अपना जितना वोल्टेज बढ़ाएंगे वो सारा का सारा करंट को, कैरियर्स को एक जगह से दूसरी जगह तक ले जाने में काम आएगा। So that's why the V has become directly proportional to I। जितना V बढ़ाया उतना I बढ़ गया, and that all because of this we are having this situation। तो concluding remark क्या रहा? Concluding remark ये रहा, it only drops voltage across junction when it has a depletion। How much voltage required to remove the depletion? 0.7। After 0.7 the drop, no depletion, then definitely it requires no voltage, it becomes short circuiting condition, like ideally short circuiting, and you know that under short circuiting there is no drop of voltage। So this short circuiting condition tells you that now there is no requirement of any voltage drop here, and whatever the voltage energy you are providing, that will only be converted to flow of current, only be converted into this one। So that's why this situation happens here। Therefore, if we see here, if we are applying a voltage, so diode only drops across 0.7, 0.2। So ideally, if you go for study this one, you get the 0.7 volt। But practically, अगर आपको लैब में ऑप्शन मिलता है करने के लिए, if you check, तो ये 0.72, 0.73, 0.74 तक चला जाता है। क्यों चला जाता है? क्योंकि लैटिस भी तो है वहां पर, डिप्लीशन तो खत्म हो गया, लेकिन लैटिस है ना, तो थोड़ा सा इलेक्ट्रॉन्स को ऑब्स्ट्रक्शन मिलेगा, तो थोड़ा सा ड्रॉप वो भी ले लेते हैं, तो 0.72, 0.73, 0.74 तक वो चला जाता है ड्रॉप। So this is exactly the meaning of this one। So I hope so now this is very much clear for all what exactly the reason behind it। Even so, well, beginning with the word potential and potential drop। So if I talk about the potential, individual word has no significance। Potential is the ability, important in simple language। पोटेंशियल किसी भी चार्ज पार्टिकल की वो एबिलिटी होती है जिसकी वजह से वो जहां है वहां रखा हुआ है। बिकॉज इट इज ऑलवेज एज्यूम्ड, हमारी जो थ्योरी है सारी की सारी, वो थ्योरी ये कहती है कि सारा का सारा जितना भी पोटेंशियल है, जितनी भी चार्ज पार्टिकल्स है, दैट आर फ्रॉम इंफिनिटी, वो सब इंफिनिटी पे कहीं रखे हुए थे या और वहीं पे जाना चाहते हैं। अगर कोई चार्ज पार्टिकल उठ के, अगर सपोज को एनी चार्ज पार्टिकल हैज कम अप हियर, अगर वो यहाँ रुका हुआ है, खड़ा हुआ है, सो दैट इज कॉल्ड एज अ पोटेंशियल। इलेक्ट्रिक फील्ड के रिस्पेक्ट में बात करेंगे तो हम कहेंगे इलेक्ट्रिक पोटेंशियल, ग्रेविटी फील्ड की बात में कहेंगे तो ग्रेविटेशनल पोटेंशियल कहेंगे। क्यों? क्योंकि इलेक्ट्रिक फील्ड कंटिन्यूअसली है और ये अपनी जगह पर रुका हुआ था, इसके पास अपनी खुद की ताकत है जिसकी वजह से ये रुका है, वरना वो इलेक्ट्रिक फील्ड इसको बहा के कहां ले जाना चाहता है, इसको इंफिनिटी पे जाके रोकेगा, क्योंकि उसके अलावा हम कुछ नहीं जानते हैं, हमारा एंड इंफिनिटी। तो अगर ये अपनी जगह पर रुका हुआ है तो इसका मतलब इसके पास कुछ पोटेंशियल एनर्जी है, सो दैट इज कॉल्ड एज अ पोटेंशियल। सो व्हाट इज पोटेंशियल? तो पोटेंशियल इज अ particular charge particle is placed at a point far distance apart from the infinity, and whatever the voltage it consists, that is called as a potential। अब हम हमेशा रेफरेंस इंफिनिटी को तो ले नहीं सकते, हम किसको रेफरेंस लेते हैं? हम तो लेते हैं एक डिब्बा है, उसके अंदर एक चार्ज पार्टिकल पहले यहाँ था, यहाँ से यहाँ आ गया, तो राइट वर्ड होता है पोटेंशियल डिफरेंस। क्यों? क्योंकि वो पहले यहाँ था, इसका पोटेंशियल कुछ था V1, फिर दूसरा पोटेंशियल यहाँ था, तो ये कहलाता है पोटेंशियल डिफरेंस। और ये जो पोटेंशियल डिफरेंस होता है, यही पोटेंशियल डिफरेंस कहलाता है ड्रॉप। क्यों? क्योंकि अगर वो यहां पर था, ध्यान से समझना, अगर वो यहां पर था, इसका अपना एक पोटेंशियल था V1, और अगर वो यहां पर आ गया, यानी कि इंफिनिटी से इसका डिस्टेंस चेंज हुआ, पहले इसकी पोजीशन ये थी, इलेक्ट्रिक फील्ड के अगेंस्ट फाइट कर रहा था और अपनी जगह पर खड़ा हुआ था, फिर जब इसने अपनी पोजीशन को चेंज की तो ऑब्वियसली जो पोटेंशियल यहां था वो यहां नहीं होगा, डिफरेंट हो गया। अब ये यहां पर खड़ा है तो V2 पोटेंशियल हो गया और अपनी पोजीशन को लेके खड़ा हुआ है, it is fighting against the electric field. So अब यहाँ से यहाँ आने में या तो इसने कुछ गेन किया या यहाँ से आने में इसने कुछ लॉस किया। तो जो भी इसने गेन या लॉस किया तो या तो उसने लिया या उसने दिया। So when it is giving because of shift of its position, important, when it is giving because of shift of its position, this is called as a potential drop. And when it is receiving because of shift of its position, it is called as a potential gain. So we have basically the two words, one is the potential drop and other is a potential gain. So energy sources that do we have like battery, like AC supply, that create potential gain. और जो हमारे पास में वैसे होते हैं रेजिस्टेंस हो गए, डायोड्स हो गए, ये एक जगह से दूसरी जगह जाने में उसकी एनर्जी को वेस्ट कराते हैं एंड बिकॉज ऑफ दैट दे ड्रॉप गेट सम ड्रॉप्स और वो ड्रॉप कहलाते हैं पोटेंशियल ड्रॉप्स। आई होप सो this might be very much clear now, the potential difference and potential drop and potential gain. So this diagram simply indicates this is a forward bias characteristic, and the forward bias characteristic shows initially the current starts moving very slowly, or we say this is almost negligible current, but once it reaches to the knee voltage, then there's an immediate hike in the current. Immediately the current starts flowing so fastly, and we say at this situation diode has no depletion region and it is in conducting mode. So below this it is not in conducting mode because that small current is not going to do anything. अगर ये डायोड हमने लगा दिया किसी बल्ब से पहले और नी वोल्टेज से कम वोल्टेज दिया तो वो बल्ब जलेगा ही नहीं, तो we say almost there is no current. लेकिन अगर हमें बल्ब को जलाना है, if we want to lit that LED, तो हमें इस नी वोल्टेज के ऊपर ले जाना पड़ेगा, then we say yeah it is working like a on switch. So this is exactly the on and off state. Similarly, if we go to the reverse bias situation I have already told in the previous one. What is the reverse bias situation? We are just changing the polarity of battery. While we are changing this polarity of battery, under this situation what happens? Depletion region keep on increasing, बढ़ती चली जाएगी, सीधी सी बात है। Depletion region बढ़ेगी तो वोल्टेज का ड्रॉप, यू सी हम अपोजिट डायरेक्शन में वोल्टेज बढ़ा रहे हैं, अपोजिट डायरेक्शन में वोल्टेज बढ़ाने से अब देखो आपका ये रिवर्स बायस वोल्टेज है डायोड के अक्रॉस, इट इज कीप ऑन इंक्रीजिंग, ये रुका नहीं, बट एट अ सर्टेन पॉइंट वी सी हियर अ टर्मिनोलॉजी इज रिटन एज VDR। एक लिमिट तक जब हम डिप्लीशन रीजन को पे वोल्टेज बढ़ाएंगे इट कीप ऑन इंक्रीजिंग, और इस पे इतना हैवी इलेक्ट्रिक फील्ड सेटअप हो चुका होगा, इट हैज जस्ट बीइंग लाइक दैट। सो वंस इफ वी रीच अ सर्टेन लिमिट, एक लिमिट होगी ना जब तक वो डिप्लीशन रीजन इंक्रीज होगा, strain वो झेल पाएगा। Once we reach at a certain point, then at this situation, the covalent bond which were the part of depletion region, जो depletion region के अंदर covalent bond बने हुए थे, उन पे इतना heavy electric field लगेगा कि वो एक साथ सारे टूटने लग जाएंगे। The breaking of the bonds starts, and at that situation we call now the breakdown has become। यहाँ पर क्या हो गया? breakdown हो गया, covalent bond टूटने लग जाएंगे, junction टूटने लगेगा, और वो कोवेलेंट बॉन्ड टूटते जैसे चार्ज पार्टिकल्स फ्री होंगे, इलेक्ट्रॉन्स विल स्टार्ट्स मूविंग एंड होल्स स्टार्ट्स मूविंग। आफ्टर दिस ब्रेकडाउन इमीडिएटली current start rising so heavily, and if you see here this is the IR which is in microampere order, and the reverse bias direction current flows. So if you want to use your diode in the reverse bias situation, अगर reverse bias situation में यूज करना है तो उसको उसका ब्रेकडाउन वोल्टेज पता कर लो कि भाई 50 वोल्ट है, 45 वोल्ट है, 30 वोल्ट है। After 30, after 40, after 45, it will become breakdown. इसके बाद यूज करोगे तो दोबारा डायोड काम में नहीं आएगा, खराब हो जाएगा, जंक्शन एब्रप्ट हो जाएगा। तो उसके अंदर ही अंदर अगर आप इसे यूज करोगे, so in reverse bias it is off, in forward bias it is on. If you see here, a small current is flowing, microampere है लेकिन बहुत small current है, that small current is called as a leakage current. That is called as a leakage current. And you know what is the reason behind the leakage current? I'm leaving this question on you, so you just find, and I'll ask this question in the next lecture. If you know that, you can just share me right now. This is called as basically the leakage current. It has a very specific and very simple reason why this leakage current we have. So if you have this answer, let me know. We study characteristic because of the reason that characteristics tells कि जब इस device को कहीं लगाएंगे तो ये कैसा behave करेगी voltage और current।